Now that we know basically all of the general rules pertaining to limits, let's take a look at one extended example. So what we have here is a function given both graphically and in function form. And we're being asked for 11 different limits. Let's take a look at the first three, which we can group together because it's the limit as x approaches 5 just from the different directions. Now, before we look at the graphics, let's just go ahead and put this in. Put in 5. And what we're going to get is 25 plus 30 plus 8, which is 63. In the bottom, we're going to get 0, 25 minus 15 minus 10. So we know that this is going to be positive or negative infinity. Here's where looking at the graph is going to help. We can see that from the left side, as we approach 5, we're going toward negative infinity. From the right side, as we approach 5, we're going to positive infinity. Which means that the limit as x approaches 5 does not exist because these two things are not equal. Let's then take a look at as x approaches negative 2 from the left, the right, and in general. Now negative 2 is here. And again, let's go ahead and put them in first. I'm again going to change the color here. So we put in negative 2 over 2 plus 6 times negative 2 plus 8 all over negative 2 times 2 minus 3 times negative 2 minus 10. 4 minus 12 plus 8 is 0. 4 plus 6 minus 10 is also 0. So this is an indeterminate form, which means, and we can see it visually here, that there's a hole here rather than an asymptote. So how do we deal with that? Well, visually it's pretty tough to say exactly what that is. So why don't we factor the top and the bottom here and just remove the hole. So we've got x squared plus 6x plus 8. Let's factor that over here. We're going to get x plus 4 times x plus 2. And in the denominator, we're looking for two numbers that add to negative 3 and multiply to negative 10. So we're going to get x plus 2, x minus 5. And we can divide out the x plus 2's. So now we're left with just x plus 4 over x minus 5, and we've removed that hole. So now we can put in the negative 2 into that. We've got negative 2 plus 4 and negative 2 minus 5. So we've got 2 over negative 7, positive 2 over negative 7. So it's negative 2 sevenths. Now there's no way you would have been able to tell that visually, which is why we need to use both tools here. Now also notice that because it's a hole, the left and the right-hand limits are both going to approach that value, which means that all three of these are negative 2 sevenths across the board. Then we're going to do 0 from the left, the right, and in general. Now notice here that at 0, there does not appear to be a hole. There does not appear to be an asymptote, so let's just try filling in. And we should always try filling it in first anyway. So put in a 0. And we've got 0 squared plus 6 times 0 plus 8, which is just 8, over 0 squared minus 3 times 0 minus 10, which is negative 10. So we've got negative 4 over 5. And since we're continuous at that point, all three of these are just negative 4/5. Finally, we've got the limits as x approaches infinity and negative infinity. And here we want to take a look at this graphically. You see, it appears we have an asymptote, but it's somewhat difficult to determine what that asymptote is. So let's remember our rule. For infinity, we're going to have the coefficients of the highest powers if the powers are equal. The highest power is in fact equal. Both the coefficients are 1, so our asymptote must be 1, which means that the limit as x approaches infinity is positive 1. Now, in this particular case, we can also apply that to the negative. Because there is no negative here, both powers are x squared. So when I take the negative and square it, I get a positive. And the denominator is also a negative squared, so that's a positive. So when I put those over each other, I'm going to remain at positive 1 and not negative 1. And that's basically limits up to this point in one extended example.